Okay, we're going to talk about ionic bonding. So in ionic bonding, electrons are transferred from one atom to another. And they're transferred from a metal atom, because metals always want to lose electrons because they've got like 1 or 2 electrons in their outer shell. So to become like a noble gas, they want to lose one. And they transfer them from a metal to a non-metal, because non-metals are always have almost full out shells, 1 or 2 short of a full outer shell. So by gaining another couple of electrons or 1 electron, they can acquire a noble gas electronic configuration. So let's have a look at sodium. Here we've got a sodium atom here. Okay, and the sodium is atomic number 11, so that means it's got, in a neutral atom, it's got 11 protons and 11 electrons. So it's going to have 2 in the first shell, that's full up. Then it's going to have 8 in the second shell, so that gives us 10 electrons. And in the last shell, it's going to have 1, so it's now got 11 electrons. So you can see sodium really wants to lose that electron. And let's look at chlorine. Here we've got a chlorine atom. It will react with sodium. And chlorine is atomic number 17, so that means it's got 17 protons, so 17 negative electrons in a neutral atom. So it has 2 in the first shell, 8 in the second shell, which takes us to 10. Now I'm drawing these ones as dots. Are they any different to the sodium electrons? Obviously they're not. It's just to show you where they're going to, where they come from. And so that means you've got 7 in the outer shell. So you can see that chlorine really wants to gain 1 extra electron so you can have noble gas electronic configuration. So let's see what happens when they react then. Okay, so sodium is going to lose 1 electron, so that will mean it's going to have just 2 in the first shell. Oops. 2 in the first shell and 8 in the second shell, so it's got a full outer shell. It's like it's got the same electronic configuration as the noble gas neon now. So, okay, but it's no longer neutral because it's still got 11 protons in the nucleus, but it's got 11 plus protons, positive protons. It's now only got 10 negative electrons. So that means it has an overall charge of +1. So we put a plus up there. And we don't call this a sodium atom anymore because it's not neutral anymore. We call it a sodium ion. It's a positive ion. Okay. People always feel at first it's a bit weird. You know, you lose something, you lose an electron and become positively charged. Well, it's because you're losing a negatively charged electron. Okay, so let's see what happens with the chlorine. The chlorine is obviously going to gain that electron, and it's this electron that, you know, that's come from the sodium ends up going to the chlorine. So here we've got Cl. The inner shells are the same, so you've got you end up with 2 in the first shell, 8 in the second shell, and it's got 7 of its own electrons in the outer shell, plus this one here, which I've drawn as a cross, which has come from the sodium atom. And you can see that the chlorine is no longer electrically neutral because it's still got 17 protons, which are plus, but it's now got 18 electrons, which are minus. Okay, so that means we're going to have a minus charge up there. Quite often draw a circle around it just to make it a bit clearer. And this is a chloride ion. Now you've got 2 oppositely charged ions there, and they are going to attract to each other, and that is what a basically an ionic bond is, right? And I don't really like the term ionic bond That's a picture. I'll show you, explain what this is in a minute. So you can call it an ionic bond. That suggests it's like a stick, like it's directional. What holds it together is the strong electrostatic attraction between positive ions and the negative ions. And they were the words I'd use in the exam as well. Strong electrostatic attraction. Okay. Right, so how are they arranged then? Now, there is a bit of a, quite often people have this incorrect idea that they think that sodium, because the formula is written down as NaCl, that it's somehow like a molecule of sodium chloride, and you have one sodium stuck to one chloride. That is not what happens. You get billions of sodiums, and they're shown them in this diagram as those little crosses there, as those little spheres there. They are smaller than chloride ions. They've got less shells, and you can see each sodium is surrounded by the negative chloride ions. They've only shown a very, this is actually taken from the AQA specification, that picture. They've only actually shown a very, very small part of how the ions are arranged. You've got to imagine that even the most microscopic bit of salt, sodium chloride, is going to have billions of atoms. That pattern just carries on repeating itself. And that is called, this is called an ionic lattice. And as I say, there's very strong attractions, strong electrostatic attractions between the opposite ions. So it's got a very high melting point. Sodium chloride has and all ionic compounds have very high melting points because of the very strong forces of attraction between the oppositely charged ions. Now, there's another way of showing this ionic lattice. That is good because it's showing the ions the true size and how they're packed, but it's not very easy to see how they're arranged there. So if you want to see a bit more easily, you can sort of expand it and sort of explode the diagram. So if you draw a cube like this, I'm going to divide that cube up like this. Now, if I draw my chloride ions, that's supposed to be a chloride ion, and I draw my sodium ions as the blue, Na plus ions, you'll see they're arranged like this. So every time you have a sodium ion there, it's going to be surrounded by 4 negative chloride ions. And don't forget, it's really 6 because there's one behind in the cube you can't see, and then there's one coming out of you, out of the cube towards you as well. So there's going to be 6 negative chloride ions around each sodium, and vice versa. Okay, so if you wanted to, that would be a sodium ion there, sodium there, there and there, and the chlorides would be here. Carry on doing the rest of that structure, and the sodiums will go there. So that's what how the ions are arranged in sodium. This is a model of the NaCl ionic lattice. It's as I say, it's the ions are not really shown their true size, but it's a bit easier to see the arrangement than it is from this more correct space filling model that you've got up there. Okay, so ionic compounds then. Ionic compounds also, importantly, they're very high melting points, but when you do melt them, they will conduct electricity. But only when molten. Now, when they conduct electricity, a lot of people think, oh, electricity is the flow of electrons, which is true. Usually it is, but strictly speaking, electricity is the flow of any charged particles. Well, in this case, when ionic compounds can conduct, it's the flow of charged ions. But they will conduct electricity, but only when they're molten, because of course when they're solid, the ions can't move. They're not free to move. They're in fixed positions. Okay, so if you set up a circuit, so there's my battery, here's a light bulb, here's some electrodes, probably made out of graphite. It's a high melting point, but will conduct electricity. And if you put this in, so this is molten sodium chloride in there, the light bulb here will light up. Okay, there's light coming off that light bulb because the sodium chloride will conduct. And as I say, in there, it is not ions, it is not electrons that's conducting the current, it's the flow of ions in there. Okay, so that is the introduction to ionic bonding. So when electrons are transferred from one atom to another.